In this video, we're going to talk about optimization. So this is using techniques that we used before to find extreme values of functions, but now we'll do it in context of maximizing or minimizing some particular value. So here's an example. If a rectangle has side lengths x and y and a total perimeter of 24 inches, what are the side lengths x and y that maximize the area of the rectangle? So let's just draw a picture to see what we're talking about. We've got a rectangle, and it has side lengths x and y, and we're trying to maximize the area. So the area is x times y, and this area is what we are trying to maximize. So we know that we can find extreme values of a function by taking its derivative, setting it equal to 0, and then testing to see if those are maxes or mins. But right now this has two variables, and those variables are x and y. And so in Calc 1, we don't learn how to take derivatives with two variables. Later, when you do multivariable calculus in future courses, you'll be able to take derivatives and integrals with functions with multiple variables, but for now, we can't do that. So we need to find some equation that relates x and y together and then substitute in. Luckily, we do have another piece of information that the total perimeter of the rectangle is 24 inches. So remember that the perimeter of a rectangle or of any shape is just the total length of all of its sides. So the perimeter in this case would be, there are two sides of length y and there's two sides of length x. So the perimeter is 2y plus 2x, and we're told that the perimeter is 24 inches. So we could solve for one of those two variables. Let's solve for x. And so we've got dividing both sides by 2 gives us y plus x equals 12. And now solving for x, let's say we'll solve for y actually. Y is equal to 12 minus x. So we're solving for y so we can substitute that value into the function for area. We can substitute y in, and then that means that area is equal to x times y, but y is 12 minus x. And so now we have a function for the area of this rectangle that's in terms of just one variable. So again, we still want to maximize this function. And to maximize it, we can take its first derivative. A prime is, let's rewrite this as 12x minus x squared. And now we can take its first derivative. Its first derivative is, derivative of 12x is just 12, minus derivative of x squared is 2x. And so that is A prime. To find its extreme values, we can set that equal to 0 to find its critical numbers. And if we do that, then we've got 12 is equal to 2x, and solving for x, we have 6 is equal to x. So 6 equals to x is our only critical number. We should verify that this is actually a maximum. Is this actually max for the area function? Because remember, a critical number could give you a max, could give you a min, or could actually give you neither, right? So let's verify that. One way we could do that is to do the first derivative test and look at values on either side of 6. We could plug in 7 and plug in 5 into A prime and see whether it was positive or negative on either side. That would be the first derivative test. Or we could do the second derivative test, which I think is easier in this case, and look at the second derivative of the area function, A double prime. So our first derivative was 12 minus 2x. That means our second derivative of 12 is 0, derivative of negative 2x is negative 2. That means that this is concave down because this is always negative. This is always less than 0, and therefore the whole function is concave down. What does it mean to be concave down? It means it's shaped like this. And remember, by the second derivative test, if the first derivative is 0 and we're concave down, then this must be a relative max for the function. And in fact, since it's always concave down, this is not just a relative max, but it's also an absolute max. Okay, so we have verified that the value x equals 6 is, or gives, a max for the area. So we know that one of the side lengths of this rectangle is x equals 6. And we know that we got an equation for y. Y is equal to 12 minus x. So in this case, y is equal to 12 minus 6. Y is equal to 6. So we now have the side lengths that maximize the area of this rectangle. And those side lengths are x equals 6 and y equals 6. So our side lengths tell us that the lengths that maximize the area of the rectangle given the perimeter, are actually the side lengths that make this square. And this is true actually for any perimeter that we start with. So given perimeter, a square always maximizes the area of a rectangle. So if you have a total side length, sum of the side lengths, then the square will always give you the maximum area of the rectangle. And in fact, you could have done this whole problem with 2x plus 2y equals p perimeter. Just let that be a constant. And if you had done that, then you would have gotten x equals p over 4. That x is equal to the perimeter over 4. And so, yeah, the side lengths would have been equal. They would have all been of size p over 4. Cool. So we were able to prove using calculus that a rectangle with a given perimeter with maximum area will always be a square. That's kind of neat. Let's think about the process that we used above and just the general approach to solving optimization problems. So the first thing that we did was try to understand the problem and draw a picture representing the different variables and the connections between them. So what are the variables and what are you trying to maximize and minimize? You then want to write an equation describing what you're trying to maximize or minimizing. So we did that above as well. That was area equals x times y. And if this equation is already in terms of one variable, then you can go to the next step. But if it's in terms of more than one variable, like we were above, we had a equals x times y, and we can't take derivatives yet with two variables. So we need to figure out some relationship between the variables and substitute. So we found a relationship based on the fact that we knew that 2x plus 2y was equal to the perimeter, and we solved for y and substituted into that original function. So we can substitute in the equation that you're trying to maximize or minimize. We then find the critical numbers, potential maximums and minimums, using the first derivative. We keep the domain in mind. So we didn't really have to worry about it in the last problem, but sometimes you might find more than one critical number, and it might not be in the domain. So for example, a side length can't be negative. So if you had a critical number of, negative something, and this was supposed to be a side length, then throw that out. That's not in the domain of the possible side lengths for that variable. We then want to verify that the value gives an actual max or min, whichever one you're looking for, using the first or second derivative test. Up above, we use the second derivative test. So remember that if we're concave down, then this is going to be a max, and if we're concave up, then this is going to be a min, and concave down means the second derivative is less than 0, concave up if the second derivative is greater than 0. We can also use the first derivative test points before and after, and if we're increasing and then decreasing, then we've got a max. If we're decreasing and then increasing, then we've got a min. So we could use either the first or second derivative test to verify that the value gives her a max or a min, but don't forget this step, it's easy to forget. And then identify all relevant values asked for in the problem. So like above, we were sort of almost done when we figured out that x equals 6, but we still needed to find the side length of the other side, and in this case it was 12 minus 6 equals x. And so our side lengths in the problem above were x equals 6, y equals 6. All right, so that's our general procedure for solving an optimization problem. Here is an example for you to try. So a box with a square base and an open top, so that means there's no top but there is a bottom, must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that maximize the amount of material used. So dimensions, width, height, and it's a square base, so the width and length of the base are going to be the same. So find the dimensions of the box that minimize the amount of material used. So we're trying to minimize the surface area of the box, and we know the volume. So I'd encourage you to grab a piece of paper, start by drawing a picture, and think about what equations you have that relate these variables to each other and what you are trying to, in this case, minimize the surface area of this box with an open top. All right, so we're going to start by drawing a picture. We have a square base. So the square base, all the side lengths on this square base are the same. And it's a box, so it has some height to it, h. So here is my box. So there we go. And one of the top is open. So top is open or empty. There is no top, but there is a bottom. So we've got 4 sides and a bottom. And we are trying to minimize the surface area of this box. So what is the surface area of the box? Well, like I said, we've got the base, and so the base of this box is x times x. The surface area of the base is x squared. And then we've got 4 sides of this box. So we've got 4 sides, and the sides have height h and base x. And so each of those has area x times h. So there's 4 sides of area x times h. So the surface area of the box is x squared plus 4xh. And that is what we're trying to minimize. Do we have any other information here? Yes, we also know that it's got to have a volume of 32,000 cubic centimeters. So we also know the volume of this box. And the volume of some kind of rectangular solid is the length times the width times the height of that thing. So in this case, the volume is x is one of the side lengths, x is another one of the side lengths, h is the height of the box. Again, because this is a square base, so the length and the width of the base are the same. So our volume is x squared times h. All right, so now we've got all of our equations. I guess we've already started to do this. So we've got an equation describing what we are trying to maximize or minimize. We know that the surface area is x squared plus 4xh, and we are trying to minimize this. But again, we have an issue where we have 2 variables. We have the variable x and we have the variable h. And so we want to solve for one of the variables. Let's solve for h. And to solve for h, we can use the fact that we have this other equation. So we have the volume is equal to x squared h, and actually the volume is equal to 32,000 cubic centimeters. So I'm going to leave off all the units for now, and we'll reintroduce the units when we finish. So for solving for h, that means that h is equal to 32,000 divided by x squared. So that's what h is, and we can substitute that back in to our equation. So surface area, the thing that we are trying to minimize, is equal to x squared plus 4xh, and then h is 32,000 divided by x squared. So we could simplify that just a little bit. The surface area is equal to x squared plus, so we've got an x and an x squared. We could cancel some things out. I'm going to leave this 4 times 32,000 here. I'm just going to leave it as that unsimplified, but I am going to cancel out my x with one of the x's in the denominator. So that is my surface area. And this is what we're trying to minimize. So we now want to take the first derivative of the function we're trying to minimize. We want to find the first derivative of the surface area. So surface area derivative, what is that? To find the derivative, I'm going to first rewrite this as x squared plus 4 times 32,000 times x to the negative 1, so that I can use a power rule instead of the quotient rule. So the derivative of x squared is 2x plus constant multiple rule, 4 times 32,000. Again, I could multiply that, but I'm sort of hoping some things will cancel and I won't have to, or I can simplify it differently later. Okay, so 4 times 32,000, constant multiple rule, times the derivative of x to the negative 1. The derivative of x to the negative 1 is negative 1 times x to the negative 2, just using the power rule. And so I could simplify that a little bit. SA prime, the derivative of the surface area is 2x minus 4 times 32,000 divided by x squared. Again, I'm leaving some stuff not simplified, but this is just personal preference. Now, to find the critical numbers, I need to set this equal to 0 and solve for x. So if I'm solving for x, one thing that I could do is add to the other side. 2x is equal to 4 times 32,000 over x squared. Now, to continue trying to solve for x, I can multiply both sides of that equation by x squared. So I've got 2x cubed equals 4 times 32,000, getting that x squared out of the denominator. Now I can divide both sides by 2. So x cubed is equal to 2 times 32,000, that's 64,000. And now to solve for x, I can take the cube root of both sides. X is equal to the cube root of 64,000. I could either do that in a calculator or I could think a little bit. So I know that 4 times 4 is 16, times another 4 is 64, and 10 times 10 times 10, 10 cubed is 1,000. So that means that 40 cubed is 64,000. Okay, and so that means that x is equal to x is equal to 40 is our only critical number. So that is our only critical number. And now we want to verify that this value actually gives us, in this case, we are trying to minimize the surface area. So we're trying to minimize the surface area. We want to verify that that's what this is doing. And again, I think it's easier to use the second derivative test here to verify that this is actually a minimum. So that means we can take the second derivative of the surface area double prime, the second derivative of this function. So the derivative of 2x is just 2. The derivative of 4 times 32,000, so plus 4 times 32,000 times a negative 1 times x to the negative 2. The derivative of that is negative 2x to the negative 3. Okay, that's all kind of messy, but all we care about is whether it's positive or negative. So we have 2 plus 4 times 32,000 divided by, times another 2, I guess, divided by x cubed. And notice that these negatives cancel out. So when x is greater than 0, which is all the time that we're interested in, this second derivative is going to be greater than 0. We're only interested in situations where these side lengths are non-negative. So f double prime of x is greater than 0, or the surface area is, the second derivative of the surface area is greater than 0. So this is concave up. So we're talking about something that's concave up. And as we know, when we're concave up and the first derivative is equal to 0, that must be a relative minimum. And so that is really, this really does give a minimum. And so we know that x equals 40 gives a min for the surface area. And now we want to identify all relevant values asked for in the problem. So remember that this was some box with a square base and an open top. And so we had x is is the length of the base, and h is the other thing that we need to solve for. So our height is given by, we solved for the height above. We found that the height was 32,000 divided by x squared. So that means the height in this case is 32,000 divided by 40 squared. And 40 squared is 1,600. So now we can divide, we can cancel out two of those zeros. And so we've got 320 divided by 16. That's 320 divided by 16. 32 over 16 is 2, so that's 20. And therefore, the height of our box is 20. Now we can come back to the units in our problem. So it asked for the dimensions of our box. This was originally cubic centimeters. This is originally in centimeters cubed. So the dimensions of our box are going to be 40 is the base, centimeters by 40 is also the side length of the other base, centimeters by the height is 20 centimeters. And so the box we've drawn isn't really correct. It's really wider than it is tall. So our box is wider than it is tall, and maybe looks like this. The height is half of the length of the base. So that is our box. And again, this minimizes the surface area for an open box with volume equal to 32,000 centimeters cubed.